There is a version of reality in which nothing about your life changes. Your room is the same, your name is the same planet turns under the same sun, the same stars hang above your city tonight, the same people move through the same streets with the same private hopes and quiet griefs. In that reality, you are sitting exactly where you are now, and yet one thing is different. A word you never said is spoken. A hand you never held is taken. A door you passed by is opened. A signal in a distant detector flickers differently. A particle falls left instead of right. A star forms sooner. A galaxy spins another way. Somewhere, so far beyond our cosmic horizon that no light from it can ever reach us, entire laws of existence may unfold under different conditions. Somewhere else, if one reading of quantum theory is taken seriously, another you keeps living out the paths this version of you never took. For most of human history, ideas like that belong to mythology, religion, dreams and fiction. Hidden realms, mirror worlds, celestial doubles, parallel destinies. They were stories told around fires and under domes of stars by people trying to make sense of chance, suffering, and the stubborn feeling that reality was larger than it looked. Then, slowly, something strange happened. The multiverse stopped being only a story. It did not become a proven fact. It did not step out of fantasy and settle cleanly into the firm territory of established science, but it entered a far more uncomfortable place. It became something that serious physicists could not always avoid. Not because they wanted a dramatic idea. Not because the universe needed a better marketing team. But because, in trying to explain the world we actually observe, some of our best theories began to hint at something far larger than a single cosmos. Inflationary cosmology suggested that the violent expansion of the early universe may not have happened just once. Quantum mechanics, interpreted one way, suggested that reality does not collapse into a single outcome at all, but unfolds into many. String theory, does searching for a deeper foundation beneath matter and forces, seem to allow not one elegant universe but an enormous landscape of possible ones, and the eerie precision of our own universe, so delicately balanced for complexity, stars, chemistry and life, push some thinkers toward an unsettling possibility. Perhaps we're not in a uniquely designed cosmos, but in one habitable pocket among an incomprehensible multitude. This is where the multiverse lives now, not in certainty, not in proof, but in the borderland between what equations permit, what observations imply, what philosophy can tolerate, and what the human mind can barely endure. Because the multiverse is not just a theory about space. It is a theory about selection, about why reality looks this way instead of another, about whether probability is fundamental or merely local, about whether identity is singular or distributed, about whether the laws of physics are necessary, contingent or environmental, about whether existence has one stage or infinitely many. And once you let the idea in, truly let it in, it begins to reach into places far beyond cosmology. If there are many universes, what exactly counts as a self? If there are branching futures, what does choice mean? If every possible outcome exists somewhere, what becomes of chance, uniqueness, and regret? If our universe is only one bubble in a far larger structure, what does the universe even mean anymore? Tonight, we're going to follow that idea all the way down, not as science fiction, not as mysticism in scientific clothing, and not as an excuse to blur the line between wonder and truth. We're going to separate what physics knows from what physics suspects, what mathematics suggests from what observation supports, what remains disciplined speculation from what dissolves into philosophy. We're going to meet the people who gave this idea its most powerful forms. We're going to enter the strange machinery of inflation, quantum theory, extra dimensions, anthropic reasoning, and the hidden difficulty of testing realities we may never reach. And as we go, the question will change. At first it sounds simple. Could there be other universes? But by the end, that is not the question at all. The real question is more disturbing. When science stares deeply enough into the structure of reality, does it find one world, or does it find that what we call the world was only a local accident, a provincial patch of something immeasurably bigger? Because if the multiverse is even partly real, then existence is not merely vast, it is plural. And the moment reality becomes plural, everything we thought was central begins to move. The human urge to imagine other worlds is older than science, older than mathematics, older even than written language. Before there were telescopes or particle detectors, before there were equations describing quantum fields or space-time curvature, there was a much more primitive encounter. The confrontation between the visible world and the suspicion that it was incomplete. The horizon looked final, but every journey proved it was not. The night sky looked fixed, but its patterns shifted with seasons and time. Dreams produced convincing realities from nothing. Mirrors duplicated the world in reverse. Memory preserved vanished moments. Imagination generated places never visited and people never born. Again and again, human beings learn the same lesson. What appears whole is often only partial. That instinct left traces everywhere. You're in cosmologies that layered heavens above heavens, in underworlds, spirit realms, divine domains, and worlds behind the visible one, in myths of doubles, shadows, twin souls, and alternate fates. These were not multiverse theories in the scientific sense, but they reveal something important. The idea of a single, self-contained, absolute world has never sat naturally inside the human mind. We are creatures who suspect overflow. We sense hidden rooms in reality. Much later, when philosophy began to harden into systematic thought, some ancient thinkers started to ask whether the cosmos might be far bigger than common experience allowed. Atomist philosophers in ancient Greece imagined infinite space populated by innumerable worlds. These were philosophical constructions, not empirical conclusions, but the leap itself mattered. If matter is built from basic units and there is no privileged center to everything, why assume one world is all there is? Centuries later, Giordano Bruno would speak of innumerable suns and innumerable earths, not all identical, but all participating in a boundless creation. Bruno was not a modern scientist, and it would be a mistake to retroactively turn him into one. But his intuition was radical. The visible heavens may not be a decorated ceiling above a chosen world, but one region among many in an endless reality. That intuition was metaphysical, poetic, theological, and dangerous. Then came the great displacements. Copernicus removed Earth from the center of the cosmos. Galileo showed that heavenly bodies were not perfect crystalline symbols, but physical worlds with texture and change. Newton replaced the intimate cosmic drama of ancient tradition with universal laws operating everywhere. The stars became suns. The Milky Way became one galaxy among many. The universe grew, and with every increase in scale, humanity became less central. That pattern matters because the multiverse, in some sense, is the next displacement. It threatens to do to our entire universe what astronomy once did to Earth. It takes what seemed like the whole and turns it into a part. But science does not move forward on emotional symbolism. It moves forward when observations fail to fit old models, when equations reveal unexplained features, when deeper theories produce consequences that our intuition resists. To understand why serious physicists ever began entertaining multiverse ideas, we have to leave cultural imagination behind and look at the problem from inside modern science. The first great step was learning that the universe has a history. For most of recorded time, people debated whether the cosmos was eternal, created, cyclical, static, or alive. But 20th century cosmology transformed those ancient arguments into measurable questions. Einstein's general theory of relativity showed that space-time itself is dynamic. Galaxies turned out to be flying apart as space expands. The universe was not a static stage. It had evolved from a hotter, denser past. Then came one of the most powerful discoveries in the history of science, the cosmic microwave background. This faint bath of radiation filling all of space is the cooled remnant of an early epoch when the universe was hot enough for matter and light to remain tightly coupled. It is the afterglow of a young cosmos, a fossil signal from a time when the universe was only hundreds of thousands of years old. With it, our cosmology ceased to be mostly speculative. The early universe left evidence, and yet that evidence created a problem. Actually, several problems. Why is the universe so geometrically flat on large scales? Why are regions of the cosmic microwave background that are too far apart to have ever exchanged information so nearly the same temperature? Why do we not see heavy relics predicted by some high-energy theories? Why does the large-scale structure of the universe begin from such a smooth, precise state, with tiny fluctuations of just the right kind to seed galaxies later on? To solve these puzzles, physicists proposed inflation. Inflation is not merely the idea that the universe expanded. We already knew that. Inflation is the idea that in its earliest fraction of a second, the universe underwent a period of incredibly rapid, accelerated expansion. Space itself swelled at a staggering rate, stretching tiny regions to cosmic size. A patch once small enough to fit inside a subatomic scale could become large enough to contain the observable universe. This solved several problems at once. If the observable universe came from a once tiny region that had been in causal contact before inflation stretched it, then the near uniformity of the cosmic microwave background made sense. Inflation would also flatten space, diluting curvature the way blowing up a balloon makes any small patch appear flatter. It would dilute exotic relics as well. And because quantum fluctuations in the inflationary field could be stretched to astronomical scales, inflation offered a mechanism for seeding the density variations that later grew into galaxies and clusters. It was a brilliant idea, but like many brilliant ideas in physics, once developed seriously, it became larger and stranger than first intended. Some versions of inflation do not end everywhere at once. In these models, inflation stops in particular regions where energy is converted into ordinary particles and radiation, creating local hot Big Bang universes like ours. But elsewhere, inflation continues. Space keeps expanding. New regions stop inflating and become pocket universes. Other regions keep going, potentially forever. This is eternal inflation, and the moment inflation becomes eternal, a door opens. Our observable universe is no longer the universe in total. It is one bubble, one pocket, one local reheated region inside a much vaster inflating background. Other bubbles may form elsewhere. separated by distances so immense that signals can never pass between them. They may have similar laws, or under some deeper theories, different low-energy physical properties. The total structure does not end with one cosmic domain. It proliferates. This is one scientific route to the multiverse. Notice what has happened. No one began by saying, "Wouldn't it be exciting if many universes existed?" Physicists began with puzzles in the observable universe. Inflation emerged as a solution. Then some forms of inflation, when analysed mathematically, seemed difficult to stop globally. The larger implication followed. Yeah, but that only gives us one kind of multiverse. To understand the full landscape, we need to be more careful. The word multiverse is a bundle term. It does not name one single theory. It names several quite different ideas that share a family resemblance. They all suggest that what we call our universe is not all that exists. One of the most useful classifications was proposed by Max Tegmark, who grouped multiverse concepts into levels. Whether one accepts his framework or not, it helps illustrate the diversity of possibilities. At the mildest end is a kind of multiverse that is barely controversial at all. If space extends far beyond the observable universe, and matter is distributed on large scales in roughly similar ways, then regions beyond our horizon may contain vast domains we can never see simply because light has not had time to reach us. These are not different law universes. They are more of the same cosmic space beyond our observational boundary. In one sense, this is not a true multiverse, just a larger universe. But it already teaches us something important. The observable universe is not the whole of reality. It is a horizon-limited patch. The next step is more dramatic. Eternal inflation producing separate bubble universes. These are causally isolated domains born from the same overall inflating process, potentially with different physical histories or properties. This is the version most people mean when they speak of cosmological multiverses. Then there is the quantum version, perhaps the strangest of all. Here the multiplicity does not arise from faraway cosmic bubbles, but from the formal structure of quantum mechanics itself. If the wave function never truly collapses, then all possible outcomes encoded in it continue to exist in a branching structure. This is the many worlds interpretation associated with Hugh Everett. Not one universe spawning distant copies through inflation, but reality differentiating internally through quantum evolution. Then there are proposals arising in string theory and higher dimensional physics, where an enormous number of mathematically possible vacuum states or compactification schemes could correspond to different low-energy universes. Add eternal inflation to that, and the result becomes even more varied. Different bubble universes settling into different regions of a vast string landscape. Finally, there are more abstract and philosophically extreme possibilities, such as Tegmark's idea that all mathematically consistent structures exist physically. This is no longer merely a scientific extension of known theory. It becomes a radical metaphysical picture in which reality and mathematical existence blur. These possibilities are not equal. Some are tied more closely to live areas of physics. Some are interpretations of existing formalism. Some are speculative extrapolations. Some verge on metaphysics. The first mistake in any serious discussion of the multiverse is to flatten them into one thing. There is no single multiverse theory. There are overlapping routes by which plurality enters modern thought, and because the routes are different, the motivations are different too. In cosmology, the motivation is explanatory. Why is the large-scale universe so smooth, flat, and structured the way it is? Why do some deeper theories seem to imply multiple local realizations? In quantum mechanics, the motivation is interpretive. How should we understand the formalism? What does measurement mean? Does the wave function collapse, or does reality branch? In string theory, the motivation is structural. Why does our universe have these low-energy properties? Are they uniquely determined or selected from a huge menu of possibilities? In anthropic arguments, the motivation is existential and statistical. Why do the constants of nature fall in the narrow range compatible with complexity, chemistry, stars, and observers? The deeper you go, the more you realize the multiverse is not a single answer but a pressure release valve for several difficult questions. It appears wherever physics confronts contingency. Whenever we ask why this world has these specific traits, and our theories suggest many possibilities, multiplicity enters the room. Before we go further, we need to clarify something basic but easy to miss. When physicists say universe, they do not always mean everything. Sometimes they mean everything observable to us. Sometimes they mean a causally connected space-time region. Sometimes they mean one solution of certain physical laws. Sometimes they mean one branch of a wave function. Sometimes they mean one vacuum state in a deeper theory. These are not identical. A great deal of confusion in popular discussions comes from sliding between them. Our observable universe is defined by limits of information. The cosmos has a finite age, and light travels at a finite speed. That means there is a boundary to what we can have seen since the Big Bang. Even though space may be far larger than what we observe, perhaps vastly larger, perhaps infinite, we are confined to a sphere of observability. That alone should humble us. Every statement we make about the whole is built from a local sample. Now consider inflation again. Suppose inflation happened. The evidence supporting inflation is indirect but significant. The large-scale flatness of the universe, the near-scale invariant distribution of primordial fluctuations, and the overall success of the framework in matching observations. Inflation, in broad terms, is taken seriously because it works remarkably well as a paradigm. But the exact mechanism, the field responsible, and the details of the inflationary potential remain uncertain. We do not yet have a complete, experimentally confirmed microphysical theory of inflation. This matters because eternal inflation depends on those details. In many models, quantum fluctuations can keep some regions inflating, even while others stop. The inflating background grows so rapidly that statistically, even though inflation ends in places, the total inflating volume keeps increasing. Universe production becomes endless. It is like a fire that does not spread across a forest, but instead causes whole forests to bud off, while the original combustion continues elsewhere. Local endings occur inside a global continuation. Andre Linde became one of the central figures in developing these ideas. His work on chaotic inflation and eternal inflation transformed the concept from a brief early universe event into a cosmic engine capable of generating an unending mosaic of pocket universes. Alexander Vilenkin also played a major role in exploring the implications of eternally inflating space. Yet, together with others, they pushed cosmology into deeply unfamiliar territory. But the idea created new problems almost as quickly as it solved old ones. If inflation produces infinitely many pocket universes, how do you define probabilities? If everything that can happen happens infinitely often, how do you compare frequencies? This is the measure problem. In an infinite multiverse, naive counting breaks down. Every allowed event may occur endlessly. The probability of observers like us becomes difficult to define. Different ways of regulating the infinities lead to different predictions. This is not a small technical annoyance. It is a sign that our conceptual tools may be incomplete, and yet, even with that difficulty, eternal inflation remains compelling to some physicists because it seems to arise naturally from mechanisms already invoked to explain the early universe. The multiverse is not imported from nowhere. It leaks out of successful ideas when they are allowed to run. Something similar happens in quantum theory, though by a completely different route. Quantum mechanics is one of the most successful frameworks ever created. It predicts the behavior of atoms, electrons, photons, semiconductors, lasers, chemical bonds, nuclear processes, and countless technologies with astonishing precision. And yet from its beginning, it carried an interpretive wound. The equations work, but what exactly do they say reality is doing? At the heart of the issue lies the wave function, a mathematical object that encodes possible outcomes and their amplitudes. Before measurement, a quantum system can exist in a superposition of different states. Not partly one and partly another in the ordinary sense, but in a mathematically real combination that produces interference effects. The double-slit experiment made this vivid. Send particles one at a time toward two slits, and an interference pattern emerges as if each particle behaves like a wave exploring multiple paths. Observe which slit it goes through, and the pattern changes. The act of measurement matters. For decades, the dominant practical attitude was often associated with the Copenhagen interpretation, though that phrase covers several related views rather than one precise doctrine. According to the rough textbook picture, the wave function evolves smoothly according to Schrödinger's equation until a measurement occurs, at which point it collapses into a definite outcome. But what counts as a measurement? Where exactly is the boundary between quantum and classical? Does consciousness play a role? Does apparatus suffice? Is collapse fundamental, or only apparent? The more closely one examines the traditional language, the less satisfying it becomes. In 1957, Hugh Everett III proposed a radical alternative. Perhaps the wave function never collapses at all. Instead, the universal wave function evolves continuously and deterministically. When a measurement-like interaction occurs, the observer and apparatus become entangled with the system. The different possible outcomes no longer interfere in the same way because decoherence rapidly suppresses observable cross-terms between branches. To an observer inside one branch, it appears as though one outcome has occurred and the others have vanished. But in Everett's interpretation, they have not vanished. Reality is differentiated. This became known, later and somewhat misleadingly, as the many worlds interpretation. It is important to say what this does and does not mean. It does not mean there are literal classical duplicates of our world casually floating in a neighbouring dimension that you can visit through a portal. It means that the mathematical formalism of quantum mechanics may be taken seriously without adding collapse. The apparent uniqueness of outcomes becomes local and perspectival. From the inside, we experience one branch. From the outside, if such a godlike perspective were meaningful at all, the universal wave function contains many. Why would anyone prefer such an extravagant picture? Because in one sense, it is not adding extravagance, it is removing collapse. Everett's defenders often argue that many worlds is conceptually austere. The equations evolve simply and universally. No special measurement rule, No ambiguous cut between microscopic and macroscopic. No mysterious physical process by which possibilities become one actuality. The price of that simplicity is ontological abundance. John Wheeler, Everett's advisor, recognized the power of the idea even though the scientific culture of the time largely resisted it. Later, Bryce DeWitt did much to popularize the many worlds language. In the late 20th century and beyond, developments in decoherence theory, especially the work of physicists like H. Dieter Zeh and Wojciech Zurek, helped explain why branches become effectively autonomous from the perspective of observers. Decoherence does not prove many worlds, but it makes the old measurement problem harder to dismiss with vague classical language. Still, enormous questions remain. If all outcomes occur, what grounds the Born rule, the standard quantum probabilities? Why should rational observers assign the usual quantum weights if every outcome is realized? Can probability even mean the same thing when all branches exist? What becomes of uncertainty? Several researchers, including David Deutsch and David Wallace, have tried to derive the Born rule within the Everettian framework using decision theory and rationality arguments. Others remain unconvinced. Then there is the psychological difficulty. Many worlds feels absurd because it multiplies reality on scales beyond intuition. Every quantum event with branch in structure contributes to an unimaginable proliferation. Not every trivial microscopic event corresponds to a clean storybook split, because real branching is messy and basis dependent under decoherence. But the broader implication remains: reality may be a continuously ramifying structure, and what we call our world is only one emergent branch within it. This is not the same as eternal inflation. One produces many universes across cosmological space-time. The other produces many branches within the quantum state of reality. They are often conflated in popular imagination because both speak of other worlds, but the underlying logic is different. One is a consequence of cosmological dynamics, the other is an interpretation of quantum formalism. And yet, there is a shared philosophical shock. Both deny that our experienced world is the whole story. Both suggest that what feels singular may be local. Both take the boundary of reality and move it beyond ordinary access. But before the multiverse became entangled with quantum branching in the public imagination, another branch of theoretical physics added its own version of plurality: string theory. String theory began as an attempt to describe particles not as point-like objects, but as tiny vibrating strings. Different vibrational modes correspond to different particles. Over time, the theory expanded into a candidate framework for unifying quantum mechanics and gravity. It required extra spatial dimensions beyond the familiar three, and it displayed an extraordinary mathematical richness. For a period, many physicists hoped it would produce a unique, elegant description of the underlying laws of nature. Instead, a complication emerged. The extra dimensions in string theory are not simply large hidden directions we forgot to notice. In many formulations, they are compactified, curled up into tiny geometrical shapes. The exact way they curl matters enormously. It influences what low-energy physics appears in the larger dimensions, what particles exist, what forces look like, what constants arise. The number of possible compactifications turned out to be vast. Add in various fluxes and vacuum configurations, and the number of possible consistent or semi-consistent low-energy universes became astonishingly large. This is the string landscape. Leonard Susskind became one of the prominent voices arguing that the landscape, though initially disappointing to those seeking uniqueness, might make sense in a multiverse framework. Instead of there being one inevitable set of laws, the deeper theory might allow many vacuum states. Eternal inflation could then populate them, with different bubble universes settling into different regions of the landscape. Our universe would not be uniquely selected by logical necessity. It would be one local realization among many. To some, this was a revelation. To others, it was a surrender. The hope for a final theory that predicts the exact parameters of our world gave way, at least in some circles, to an environmental view. The laws we observe may be partly like the local climate of a region in a much larger world, not absolutely unique, not arbitrary either, but selected from a wider space of possibilities by cosmological history and anthropic filtering. This brings us to one of the most controversial motivations for the multiverse: fine-tuning. When physicists examine the basic constants and parameters of nature, some seem to lie in ranges surprisingly compatible with complexity. This claim must be handled carefully. Popular accounts often exaggerate it, or present it as settled evidence of design or multiverse selection. But there is a legitimate scientific question here. If certain values were significantly different, stars might not form stably, chemistry could fail to support complex structures, or the universe might expand too quickly for galaxies to condense. Perhaps the most famous case is the cosmological constant, associated with the energy density of empty space. In naive quantum field theory estimates, vacuum energy seems as though it should be vastly larger than the small positive value we infer from cosmic acceleration. Yet the observed value is tiny enough to allow galaxies and therefore observers to exist. Stephen Weinberg argued that anthropic reasoning in a multiverse could, at least in principle, explain why we observe such an improbably small value. In a vast ensemble of universes with different vacuum energies, only those with values compatible with structure formation would host observers asking the question. This is not direct evidence for the multiverse. It is a style of explanation. It says, perhaps what looks like fine-tuning is selection bias. We observe conditions compatible with our existence, because only such conditions are observable by beings like us. Anthropic reasoning has an uneasy status. Used weakly, it is nearly trivial. Observers can only appear where observation is possible. Used strongly, it becomes a powerful filter shaping what kinds of universes are noticed at all. Some physicists see this as unavoidable once a multiverse exists. Others regard it as a retreat from predictive ambition. If anything can be explained by saying we happen to live in one of the rare life-friendly regions, then what prevents cosmology from becoming an elaborate version of that's just where we found ourselves? The discomfort is understandable. Science usually seeks deep, universal, compact explanations. The anthropic principle often feels statistical, contingent, even unsatisfying. But the universe is under no obligation to align with our aesthetic preferences. If the deeper structure of reality generates many possibilities, local habitability may genuinely require selection effects. The challenge is knowing when anthropic arguments illuminate and when they merely excuse ignorance. That challenge becomes sharper when we ask the hardest question of all. Can any of this be tested? A scientific idea is not valuable only when it can be observed directly. Quarks were not seen in the ordinary sense when first proposed. Black holes were once theoretical consequences before observational evidence became overwhelming. Gravitational waves were predicted a century before detectors captured them. Science often moves through indirect inference. The issue is not direct visibility but empirical accountability. Can a theory make contact with observation? Can it constrain expectations? Can it, even in principle, be wrong? For multiverse ideas, the answer depends on which multiverse we mean. The mildest form, the existence of regions beyond our horizon in a much larger universe, is not especially problematic conceptually. It follows naturally if space extends further than what we see. While we cannot observe those regions directly, the idea is continuous with ordinary cosmology. Eternal inflation is more difficult. The process itself may have indirect support if inflation is strongly confirmed, but other bubble universes are causally remote. Some researchers have explored whether collisions between bubble universes could leave imprints in the cosmic microwave background, circular anomalies, temperature patterns, or other signatures. Searches have been conducted. So far, no compelling evidence has been found. That does not disprove eternal inflation. It merely means one hoped-for observational handle has not produced a decisive signal. There are also attempts to connect inflationary scenarios with primordial gravitational waves, non-Gaussianities in the distribution of fluctuations, or specific features in the inflationary potential. These can constrain models of inflation and, by extension, affect how plausible eternal inflation seems, but we're still far from a clean observational fingerprint that screams multiverse. In the quantum case, many worlds is even trickier. It is often said that many worlds makes the same empirical predictions as standard quantum mechanics, at least in domains where collapse models are not modified. If so, then choosing between many worlds and Copenhagen-like interpretations becomes a matter of explanatory virtue rather than direct experiment. However, the landscape here is subtle. Competing interpretations differ in ontology, not always in measurable outcomes. Science does sometimes confront underdetermination like this. One formalism can support multiple metaphysical pictures. That does not mean all pictures are equally good, but it does complicate the ordinary testability story. String landscape multiverses are harder still, since string theory itself remains unconfirmed as a theory of nature. Multiverse conclusions drawn from its landscape inherit that uncertainty. If one day string theory gained strong support and its landscape structure proved unavoidable, the conversation would shift. For now, much of this remains theoretical architecture in search of empirical grounding. This is where critics become essential. Some scientists argue that multiverse reasoning is legitimate and perhaps inevitable given certain theories. Others worry that it stretches science to the breaking point. The philosopher of science question returns. What distinguishes a fertile speculative framework from a retreat into untestability? Physicist George Ellis has been among the important critical voices, a warning against drifting into claims that cannot in principle be checked. Roger Penrose has also expressed deep skepticism toward inflationary multiverse reasoning, especially where it appears to multiply unseen domains to explain fine-tuning without adequate empirical discipline. Even among those sympathetic to inflation or string theory, many remain cautious about declaring multiverse scenarios scientifically mature. The criticism comes in several forms. One is straightforward falsifiability. If other universes are forever causally inaccessible, how can we ever know they exist? If a framework explains anything by allowing everything somewhere, does it predict enough to count as science? Another is the measure problem in eternal inflation. If probabilities cannot be defined cleanly, Then extracting observational expectations becomes unstable. A third is simplicity. Many worlds may simplify the equations by removing collapse, but at the level of ontology it seems to explode reality. Is that a virtue or a vice? Opinions differ sharply. A fourth is explanatory substitution. Does the multiverse genuinely explain fine-tuning or merely relocate the mystery? Instead of asking why our constants have their values, we ask why the multiverse generating mechanism has its properties, or why it produces the ensemble it does. A fifth is anthropic overreach. Used carelessly, anthropic selection can weaken the standards of theoretical explanation. It can become a habit of saying, "We observe this because otherwise we wouldn't be here," even when better dynamical explanations might exist. These criticisms are not embarrassing obstacles to hide from. They are part of what makes the subject intellectually serious. A theory that touches the edges of observability must be pressed hard. It must survive not just wonder but discipline. And yet criticism alone does not make the multiverse disappear. The reason the idea persists is that some of the underlying scientific pressures are genuine. The early universe really does seem to invite inflationary explanations. Quantum mechanics really does force interpretive decisions. String theory really did challenge hopes for uniqueness. Fine-tuning really does remain puzzling. The multiverse is not a fashionable fantasy pasted onto physics from outside. It is what appears when several unresolved tensions begin pointing away from singularity. At this point, the question becomes philosophical in the best sense, not as a replacement for science, but as an extension of what science has made unavoidable. What kind of reality would this be? If eternal inflation is correct, then our universe is one local thermalized region in a far larger inflating structure. There may be no global cosmic now, no privileged totality we can picture from the outside. Reality is a process of continual production, with pocket universes forming like islands in an ever-expanding sea that never settles. If many worlds is correct, then the basic ontology is not a single line of history, but a branching quantum structure. The world you inhabit is real, but not uniquely real. Alternatives are not unrealized possibilities. They are realized elsewhere in the wave function. You do not stand at the center of one outcome, but inside one branch of a ceaseless differentiation. If the landscape picture is correct, then laws themselves may be partly local. What we call the laws of nature could be environmental regularities selected from a deeper space of possibilities. The dream of one inevitable cosmic code would give way to something more like cosmic geography. These are not minor revisions. They touch the ancient human desire for uniqueness at nearly every level. Consider identity. In ordinary life, we treat the self as a continuous story. Not a perfect one, not a fully transparent one, but one anchored by memory, embodiment, and lived experience. The multiverse destabilizes that simplicity in different ways. In cosmological multiverse models, there may exist observers elsewhere, perhaps even exact or near-exact duplicates if space is infinite and configurations repeat. Because the number of possible particle arrangements in a finite region is finite, given enough space, repetition becomes plausible. This idea sounds absurd, but it follows from combining finite information content in a region with sufficiently large or infinite space under certain assumptions. Somewhere unimaginably far away, another arrangement of atoms may instantiate your life again, or almost again. Not because fate likes symmetry, but because combinatorics allows recurrence when the container is large enough. Does that other observer count as you? Most people say no. Identity is not mere similarity, it is continuity. But the question reveals something. Even without quantum branching, a sufficiently large cosmos can challenge the uniqueness we casually assume. Many worlds pushes harder. If branching occurs and future versions of you inhabit different outcomes, what becomes of personal identity over time? Does one present self relate to many future descendants? Is survival distributed? When you face quantum uncertainty, are you ignorant about which future you will become? Or are you about to become all of them in different branches? Philosophers and physicists have debated these questions intensely. There is no universal consensus. But the emotional consequence is unmistakable. The self becomes less like a point and more like a tree. That has implications for choice. In everyday life, a decision closes possibilities. You chose this city, not that one. This partner, not another. This career, not the abandoned path. One comfort of ordinary life is that choice creates actuality by excluding alternatives. But in a branching picture, exclusion becomes local, not absolute. You still experience one path. You still bear consequences. Moral responsibility does not dissolve simply because other branches exist. But the metaphysical finality of choice changes. Some people hear this and think it erases meaning. If every outcome happens, why care what you do? But that conclusion is too fast. The version of you who acts still experiences a local world shaped by action. Pain still hurts locally. Love still matters locally. Justice and cruelty still structure lived reality. Here, branching does not make your branch less real. It only makes it less exclusive. In fact, one could argue that the multiverse intensifies responsibility. Your actions are not made meaningless by multiplicity. They are the process by which local realities are differentiated. What happens here still happens here. The question of death becomes stranger too. In ordinary human consciousness, mortality is anchored by singularity. One life, one line, one ending. In some many worlds discussions, a controversial idea known as quantum immortality is sometimes floated. The claim that subjective experience might continue along branches in which an observer survives. This idea is highly speculative, widely criticized, and easy to misuse. It should not be treated as an established implication of quantum theory, but its very existence shows how quickly the multiverse reaches into existential territory. A more careful lesson is not immortality but distribution. In a branching ontology, there may be no single future self to anchor traditional intuitions about survival. Different future continuations may exist with different experiences, and what matters ethically or psychologically may need rethinking. Then there is free will. If the multiverse contains many outcomes, does that rescue freedom or destroy it? Again, the answer depends on what one means by freedom. If freedom means a magical power to transcend physics, the multiverse offers no special gift. If freedom means that actions are genuine parts of causal structure, then branching or plurality need not threaten it. One might even say that multiverse ideas move us away from a simplistic picture in which only one path was ever metaphysically real. But they do not automatically settle old debates between determinism, indeterminism, and agency. They simply rearrange the stage on which those debates occur. More profound, perhaps, is the effect on meaning itself. Human beings build meaning partly through scale. We matter to each other because our lives are small enough to hold and fragile enough to lose. At first glance, the multiverse seems to crush that. If there are countless universes, countless histories, countless observers, then any one life appears negligible. but scale has always been a false judge of significance. Astronomy already taught us that the Earth is not central, yet love did not become less real. Evolution taught us that humanity emerged through natural processes, yet grief did not become less sharp. Neuroscience showed that the mind depends on the brain, yet beauty did not evaporate. The reduction of cosmic centrality has never removed lived importance. It only removes flattery. The multiverse may do the same, or it may strip away the illusion that our universe exists as the sole stage for being. But it does not follow that local meaning is unreal. It only means meaning is not licensed by uniqueness. That may be harder, but also more honest. To see how deeply this cuts, consider the very phrase laws of nature. Most people hear it and imagine something absolute, almost constitutional, the final rules of all reality. But in several multiverse frameworks, that status weakens. Our laws may be bylaws, local regularities emerging from a deeper structure. The speed of light, the masses of particles, the number of dimensions effectively accessible at low energy, the vacuum state of fields. These may not be the one necessary architecture of existence. They may be local outcomes in a wider space of possibilities. That thought is both liberating and destabilizing. Liberating because it opens new explanatory pathways. Why are things this way? Perhaps because this is one realized possibility among many. Destabilizing because it undermines the old dream that physics will culminate in one inevitable final set of equations uniquely forcing every feature of the world. Some physicists still believe such uniqueness may exist. Others think the evidence points elsewhere. Either way, the multiverse forces us to confront how much of our desire for uniqueness came not from data, but from philosophical taste. And then there is time. In an eternally inflating multiverse, time becomes difficult to globalize. There may be no universal clock covering the total structure in a clean, observer-independent way. Different bubbles have different histories. The inflating background generates new domains without a single shared chronology that means the same thing everywhere. Time remains real locally, but the total picture resists ordinary narrative. In many worlds, time intertwines with branching. History is no longer a single sequence of events, but a structure in which past entanglements generate multiple, effectively classical futures. The familiar image of one timeline becomes inadequate. These are not merely scientific curiosities, they alter the grammar of thought itself. Human language is adapted to a world of singular objects, discrete events, and local causes. The multiverse pushes against that grammar. It asks us to think in ensembles, branchings, landscapes, causal isolation, observer selection, and distributed actuality. It is one reason the subject feels so difficult. The challenge is not just technical, it is cognitive. Our minds evolved to track prey, allies, weather, danger, kinship, and social hierarchy, not pocket universes and universal wave functions. Even so, we can trace the logic. The cosmological route begins with observable puzzles, moves through inflation, and may end in eternal production. The quantum route begins with the success of the formalism, confronts measurement, and may end in branching reality. The string route begins with unification, encounters enormous vacuum diversity, and may end in a landscape populated by cosmological dynamics. The anthropic route begins with fine-tuning and may end in selection effects across a larger ensemble, different roads, similar destination. Reality may not be singular, but none of this means the multiverse is one. A mature documentary must resist the temptation to confuse intellectual seduction with scientific success. The multiverse is powerful partly because it speaks to a deep pattern in modern science. Every time we thought we'd reached the whole, we discovered a larger context. Earth became one planet, the Sun one star, the Milky Way one galaxy, the observable universe perhaps one region. This pattern creates an almost narrative momentum toward plurality. But nature does not owe us narrative symmetry. The next step is not true just because previous steps humbled us. So where do we actually stand? We stand in a state of asymmetrical uncertainty. Inflation, in some broad form, remains highly influential and compatible with data, though not fully nailed down at the microphysical level. Eternal inflation is plausible in many models, scarcely but not established. Quantum mechanics is overwhelmingly confirmed, but its interpretation remains open. Many worlds is elegant to some, excessive to others, and not experimentally singled out. String theory is mathematically rich and historically important, but unconfirmed, and its landscape remains speculative as a description of physical reality. Anthropic reasoning may explain some features if a multiverse exists, but it is not direct evidence that one does. That is the honest state of play, and perhaps honesty is more interesting than certainty here. Because the multiverse is compelling precisely where certainty ends. It is a frontier subject, where mathematical structure, empirical limits, philosophical analysis, and existential imagination all collide. To feel the full weight of that collision, it helps to return to a more intimate scale. Take a simple act, looking at the night sky. For most of human history, this was a confrontation with mystery dressed as permanence. The stars seemed fixed and final. We now know they are neither. They are born, they burn, they die. Their light travels across abyssal time. Many of the points we see are gone already. Some belong not to our galaxy alone, but to structures spread across incomprehensible distances. The sky did not become less beautiful when science explained it. Oh, it became more shocking. The multiverse threatens a similar expansion. What if the sky itself is provincial? What if all our galaxies, all our cosmic history, from Big Bang nucleosynthesis to dark energy, all black holes and nebulae and habitable planets and future extinctions, belong to one local volume inside a structure that does not fit inside ordinary imagination? There is a temptation, when faced with scale like that, to become numb, to treat large numbers and remote realities as decorative abstractions. But the scientific imagination asks something harder. It asks us to remain emotionally responsive while thinking beyond direct experience, to let scale alter us without turning into slogan or spectacle. This is especially difficult because the multiverse sits so close to the line where physics and metaphysics touch. Some thinkers embrace that contact, others fear it, but perhaps the line was never as clean as we pretended. Physics has always carried metaphysical consequences. The shape of space, the nature of time, the existence of atoms, the relativity of simultaneity, the quantum structure of matter, each changed not only equations but the conceptual world. The multiverse does the same, only more radically. If our universe is one among many, then contingency enters where necessity once stood. If many histories coexist, actuality becomes local. If observers are selected from wider ensembles, then explanation acquires an indexical dimension. Not only why this is possible, but why we find ourselves here. If laws vary across domains, then the search for a final theory becomes partly a search for the generator of local law, not merely the law itself. And if all of this proves wrong, if future physics finds unique dynamics, defeats eternal inflation, clarifies collapse, and restores singularity, then the multiverse will still have mattered, because it will have forced science to clarify what counts as explanation at the edge of observability. It will have sharpened the relationship between mathematics, evidence, and ontology. It will have shown how easily a successful formalism can tempt us into larger realities, and how carefully that temptation must be handled. In that sense, the multiverse is not just a claim about what exists. It is a stress test for scientific reasoning itself. Can science speak responsibly about what lies beyond possible direct access? Can indirect inference remain legitimate when causal contact is absent? Can explanation survive in ensembles of possibilities? Can probability be defined in infinite contexts? Can a theory be accepted for elegance alone, or must ontology bend to observability? These are not side questions. They are the questions of frontier knowledge. And there is one more. Why are we so drawn to this idea? Part of the answer is intellectual. The multiverse offers frameworks for unresolved problems. It emerges from genuine theoretical pressure. But part of the answer is emotional. The multiverse mirrors our lives in uncomfortable ways. Every biography contains lost branches. Every person lives among unrealized versions of the self. Every regret is a local ghost. Every memory is a witness to roads not taken. Parallel worlds fascinate us because we already live psychologically among alternatives. Science does not validate that emotional resonance, but it gives it a new form. It says, perhaps reality itself is stranger than singular fate. Perhaps contingency is not merely a feature of personal life, but written into the architecture of existence. That possibility can be comforting. It can also be terrifying. Comforting because it suggests abundance where we fear finality. Terrifying because it removes the protective walls of a single, finished world. And perhaps that is why the multiverse feels so alive in culture. It is not just about distant universes. It is about the instability of the real. As our journey deepens, the question becomes less, are there other worlds? And more, what kind of thing is a world? Is a world a causally connected space-time region, a branch of a wave function, a vacuum state of deeper laws, a domain selected by conditions for observers, a mathematical structure? Each answer changes the picture. The oldest human instinct was to imagine hidden worlds layered around us. The newest scientific instinct is to derive multiplicity from equations. Between them lies an extraordinary continuity, the refusal to believe that the visible is the whole. But science earns the right to believe only what its methods can support. So let us press one more time on what separates good multiverse reasoning from bad. Good reasoning begins with a successful, constrained theory that explains known data and then explores its consequences. Inflation is an example, so is the quantum formalism. So, in a more tentative way, string theoretic structure. Bad reasoning begins with desire. It starts from the wish that all possibilities exist, or that consciousness can escape death, or that every fictional world is physically real, and then retrofits science around that wish. The multiverse is especially vulnerable to abuse because it sounds like permission for anything. But real multiverse proposals are not invitations to fantasy. They are severe, mathematical, often cold constructions emerging from technical work. Good reasoning distinguishes levels of confidence. It says, this part is established, this part is inferred, This part is speculative. This part is philosophical. Bad reasoning collapses those distinctions and sells wonder as proof. Good reasoning welcomes criticism. It knows that ideas with weak observational contact need stricter scrutiny, not looser standards. Bad reasoning treats skepticism as lack of imagination. The reason this matters is simple. The multiverse, more than most topics, can either elevate scientific thinking or dissolve it. It can teach us how disciplined wonder works, or how quickly wonder becomes intellectual anesthesia. Now let us return to the physics one final time, but from the widest angle. Picture the observable universe as a sphere defined not by walls, but by time and light. Beyond it may lie more of the same. Picture inflation turning a tiny region into the vast cosmic expanse we inhabit, while elsewhere the process continues, birthing other pockets. Picture quantum fields fluctuating in the early universe, their tiny uncertainties stretched to seed galaxies, while the same quantum logic, taken seriously at all scales, refuses to collapse into one history. Yet picture a deeper theory with extra dimensions and myriad vacuum possibilities. A landscape so large that uniqueness becomes elusive. Picture observers arising only in the narrow bands where conditions permit stars, chemistry, planets, complexity, memory. Picture all of these not as confirmed truth, but as overlapping efforts to answer why reality is this way and not another. The multiverse is what appears when one answer is not enough. It is, in a sense, the shadow cast by explanatory excess. When theories are powerful enough to generate more reality than observation immediately requires, this surplus must be interpreted. Sometimes that surplus later vanishes under better understanding. Sometimes it remains and changes the map. We do not yet know which this will be. History offers both caution and encouragement. There have been times when speculative excess outran data and collapsed. There have also been times when reality turned out to be far stranger than conservative intuition allowed. Atoms, curved space-time, quantum entanglement, black holes, cosmic expansion, all were once shocking. The wise response is neither gullibility nor reflexive dismissal, but patience sharpened by rigor. So patience is what the multiverse demands, not passive waiting, but active discipline. Better observations of the early universe, better understanding of inflation, deeper work on quantum foundations, more clarity on quantum gravity and string theory, stronger philosophical analysis of probability, explanation, and observership. Frontier questions do not yield to impatience. They yield, when they yield at all, to accumulated pressure from many directions. But while science waits for clearer answers, the idea itself continues to transform the imagination. Because even the serious possibility of a multiverse changes the emotional atmosphere of knowledge. It tells us that reality may not be exhausted by what is visible, that our universe may not be the singular expression of law, but one local chapter in a wider structure, that other histories, other constants, other branches, other domains may exist, not as spiritual allegory, but as consequences of equations we already use to describe the world. And even if the final story proves more modest, something has already happened. The boundary of the thinkable has expanded. The night sky above ancient humanity inspired myths because it exceeded explanation. The cosmos of modern science inspires different kind of awe because explanation itself keeps expanding the unknown. We understand more, and the world does not become smaller. It becomes deeper. Every successful theory opens another layer of questions. The multiverse may be one of those layers, or it may be a transitional scaffold, useful now but destined to be replaced. Either way, it reveals a profound truth about human inquiry. Whenever we try to close reality into one finished picture, the edges begin to move. Now we come to the final question. Suppose the multiverse is real. Suppose that beyond our horizon, beyond our cosmic history, beyond the visible aftermath of our Big Bang, there are other universes, some lifeless, some radically different, some governed by altered constants, some branching from quantum possibilities, some formed in inflating space, some perhaps forever inaccessible. What would that mean for us? Not that we are unreal, not that our lives are meaningless, not that science has dissolved into fantasy. It would mean something subtler and, in a way, more difficult. It would mean that reality is not arranged around our need for singleness, that the world we inhabit is complete, enough to live in, but not complete enough to define all that is. That truth may be larger than locality. That existence may not come in one version. The human mind resists that because we are creatures of one branch, one body, one horizon, one biography. We wake in one room, in one era, under one sky. Consciousness feels singular because it is locally singular. But locality is not totality. It never was. Long before we knew the earth was round, the horizon looked flat. Long before we knew stars were suns, the night sky looked ornamental. Long before we knew galaxies existed, the Milky Way looked like a complete celestial river. Long before we knew the universe had a past, the heavens looked timeless. Appearance has always been provincial. The multiverse is the latest accusation against the obvious. It says the same thing in a more devastating form. Perhaps even the universe was only what the horizon made available to a local species inside a larger architecture. And still, here we are. A brief form of life on a small planet around an ordinary star, in one galaxy among hundreds of billions, in one observable universe perhaps among many, trying to understand the whole from inside a fragment. That is not a humiliation. It is one of the strangest and most beautiful facts in reality. Because whether the multiverse exists or not, the attempt to ask the question already reveals something extraordinary. Matter, after billions of years of cosmic evolution, became capable of wondering whether the laws that shaped it are unique. A local mind produced by one branch of one history can still reach conceptually toward what lies beyond all direct experience. That reaching is not proof, but it is noble, and maybe that is the deepest lesson hidden inside the multiverse debate. Not that we are destined to confirm infinite worlds, or that every possible reality secretly exists, but that the universe, whatever lies beyond that word, permits creatures like us to stand inside the known and feel the pressure of the unknown so intensely that we begin to ask whether singular existence was ever enough. There is something haunting about that, not because it makes us small. We were already small. Not because it makes us uncertain. We were always uncertain. But because it suggests that the final shape of truth may be incompatible with the instinctive human need for one center, one world, one ending. If the multiverse is real, there may be no final cosmic stage on which everything gathers into one illuminated whole. There may be only regions, branches, pockets, landscapes, observers, histories, each real locally, none complete globally, a plural reality, a fractured totality, a cosmos in which the word everything becomes almost too naive to use. And if that is true, then perhaps the most honest response is not triumph, not despair, but a kind of disciplined astonishment. To keep looking, to keep separating evidence from fantasy, to keep following equations without worshipping them, to keep resisting the comfort of easy answers, to keep the imagination wide and the standards high. Because somewhere between skepticism and awe, science does its best work. Tonight the stars above us look silent. They looked silent to the first humans too. But silence has never meant emptiness. It has only meant that reality does not speak in the language we first expected. So we build instruments, we build theories, we test, we argue, we revise. We dare to think beyond the horizon, right? And then we ask whether thinking beyond the horizon can ever become knowledge. That is what the multiverse really is. Not a settled doctrine, not a comforting fantasy, but a threshold, a place where cosmology, quantum theory, mathematics and philosophy all converge on one unbearable possibility, that the world we know is real, but not alone. And if one day the evidence sharpens, if one route to plurality survives every challenge and the multiverse passes from suspicion into accepted science, then the shock will not be that there are other worlds. The shock will be that for so long we believed one world was enough. Until then, we remain where all honest inquiry remains at the frontier, inside uncertainty, lit by reason, surrounded by darkness, listening for structure in the silence. And perhaps that is fitting. Because if the multiverse exists, it is not waiting somewhere like a hidden country beyond a border. It is already the case. Already woven into the architecture of being. Already there, whether we ever prove it or not. A vastness beyond singularity. A reality beyond the comfort of one sky. A possibility so large that even now, from one small branch of one small world, it is beginning to change the way we understand what it means for anything at all to exist.